Would you like to teach? Oh, okay. Okay, let's start because this is recording. Everybody ready? Okay, so we want to talk about weather and climate. One of the first things we need to mention is that hopefully we recognize that the places that we have on Earth, different biomes, they don't all have the same weather and climate patterns. Okay? As an example, in Lethbridge, today it's, 7 degrees and kind of overcast, maybe a little bit of sun. Pretty cold. If we were to go to Miami, Florida right now, it's probably, what was that? Well, that's true. Okay, so let's go somewhere else. Let's go to the middle of the Gobi Desert. It's probably like 30 degrees out there, right? And if we were to go to the rainforest, it's probably raining. And if we were to go to the South Pole, it's probably frozen. We've learned about the different biomes. But now we want to talk about, well, why do they all have such different weather patterns? Why are there things that are different? And it's really about this concept right here. It's about that energy transfer concept. Through these processes of conduction, convection, and radiation, energy is transferred differently to different places. It's not a fair system. Unlike where it would be nice if like everybody got $10 for their allowance, right? I have 2 little girls, and when we have to give them their allowance, they kind of want to have the same amount. It's not really fair to give one kid $100 and the other kid $1. That's really favorites. But here's the thing. Our world does play favorites. There are some places in the world. There's some places in the world where we don't get an even energy distribution. The most energy is usually found around the equator, and the tundra is found like at the North and South Poles. We want to explain why. First thing we have to mention, though, is the difference between weather and climate. Okay. Weather is more of a short-term sort of thing. Weather is like, what's it like outside today, and tomorrow, and the next couple of days. We're talking about things like what's the temperature, what's the precipitation, wind, cloud, storm, humidity, pressure. Okay, very, very short-term sort of forecast. There we go. But climate's more of a long-term trend. And we know what climate should be in various areas. For example, what do we expect to happen in December and January? I'm expecting snow. I would be very surprised if it was plus 30 outside, right? And that's just based on I've lived 30-something years of my life. I kind of know the pattern by now, right? If it's the middle of July, I'm probably not getting my parka and my snow boots out because I recognize that chances are it's going to be warm, right? That's climate. Climate is more of a long-term concept, and different places on Earth have different climates. As an example, if you live near the equator, they really don't have seasons at the equator. They just have hot all the time. They do have rainy and dry sometimes, but they really don't have massive temperature differences. Right? If anyone has been to, say, the Vancouver Island area of British Columbia, it's way less extreme there. They still get summer and winter and fall, but they don't really get a huge amount of snow usually. It's usually a lot more moderate. Okay? And so again, we're talking weather trends. That being said, can it snow in Victoria? Sure. In theory, is it possible you could have a random freak snowstorm in Brazil? Maybe. It doesn't mean that the climate has necessarily all of a sudden changed because long term it's still the same. Sometimes we have days where it's like really, 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 really hot out in the middle of December, and people all of a sudden start arguing, oh, there's examples of climate change. A really famous one happened a few years back. Maybe you've heard the story. Leonardo DiCaprio was filming a movie in southern Alberta, and a Chinook rolled through. You guys are familiar with Chinooks, right? We get these, I don't remember which one it was, the Reverend or something like that? Oh, yeah. Yeah. Anyways, I've only got 25 minutes. We got to stay on topic here. Leonardo DiCaprio's in southern Alberta. A Chinook rolls through, and he posts to social, shush, please. I know we are, but I've got 25 minutes to try to teach you something, okay? A Chinook rolls through, the snow starts to melt around him, and he posts on like social media, I am watching climate change happen right in front of my face as all the snow is melting away, and like 3 feet of snow disappeared in like 2 days. Is that surprising to us? I've seen that before. You've seen that before because that is part of our climate. But for someone who thinks that that's just a freak weather phenomenon and is like, whoa, that's crazy. I mean, people kind of make fun of him still to this day. If you've heard that story before and you go, Leo, it was just a Chinook, it's fairly normal, right? That helps illustrate climate versus weather. The idea that we know what the long-term trends are, and we're fairly familiar that weather in Alberta, we can have those Chinooks, those warm winds come down off the Rocky Mountains and basically take all the snow away with it with that warming trend. Okay. Let's move on. we know that there's also seasons. Okay? The Earth has very, very distinct seasons in some locations. Not at others, but in some. We go through a very distinct winter, summer, fall, what did I miss? Spring sort of section there. And one of the reasons why is that Earth is tilted. Earth actually has a little bit of like a lopsided bend to it. The reason why is that if the sun is over here, we don't actually get the amount of sunlight that's equitable and fair. Remember that silly example I mentioned of like one parent giving your kid $100 for allowance, the other one $1? Well, during certain times of the year, the southern hemisphere gets more sunlight. Just look at this picture right here. Here's the southern hemisphere, and they're getting way more sunlight than the northern hemisphere. Well, that's because this is winter. This is winter time for the northern hemisphere because the Earth is tilted away from the sun. And down here, this is summer for, say, Australia. If you're not familiar with this idea, when we think of winter and Santa Claus and snow and presents in December, it's still, the same month. It's still December in Australia, but it's summer for them. They're heading to the beach on December 25th. We're bundled up inside. That's a very weird concept to think of, but it's because the other half of the world gets different distribution of rays. For them right now, it's spring. Yeah, because it's fall for us, right? Here's some written notes on it. I hate reading off of slides. You feel free to read this or write it down later, but it's all about the angle of inclination. It produces unequal heating. That's really, at its core, what we're talking about. It's not fair. It's not an even distribution. During certain times of the year, some places get more incoming solar radiation. And it's really based on latitude. Okay. Here's a picture that kind of illustrates the opposite of what I just mentioned. Here's that same tilt, but let's say that the sun is now on this side of the Earth. Now, by the way, the sun doesn't move though, right? The Earth is actually moving around the sun, but if you can kind of imagine that, at one point, the Earth is on, here's the Earth on the left of the sun versus the right. What's happening during this time of year? This is now summer for the northern hemisphere. Because you can see that the northern hemisphere, here's the equator right there. Look how many lines of incoming radiation there are. I know that a line is not really a good representation of radiation, but here's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's 10 lines of radiation that get to hit the northern half of the Earth. And only 1, 2, 3, 4 that hit the bottom part of the Earth. So it's almost like for half the year, mom gives one kid more allowance than the other. And then for the other half of the year, mom gives the other kid more allowance, right? It's not really fair that the way that the Earth gets the sun amount. Okay. This is actually what leads to our major seasons, as well as a concept maybe you're familiar with, solstices and equinoxes. Solstice is either the shortest or the longest day of the year, and then the equinoxes are where you have equal day and night. We're going to be coming up on December 21st, pretty quick here, which is where we have our shortest day. Look at this picture right here. Here's North America right here. Can you see how we're not getting nearly as much sun as, say, the South Pole? Remember that YouTube video or the Planet Earth video we showed you of Antarctica? How the penguins have to go for 4 months without sunlight, but then they get 4 months of sunlight? I think this picture helps show why. Right here, lots of sunlight. Right here, lots of sunlight. Right here, lots of sunlight. But look here. Here's Antarctica over here. In the middle of June, sunlight can't reach Antarctica because it can't go through the middle of the Earth. Does that make sense? And so because of that tilt of the Earth, where the Earth is not straight, it leads to either equal days during kind of the middle of the year, during your spring and your fall, and it leads to really short days or really long days, because right here, North America is getting sunlight all the time. Over here, see how it's not getting as much sunlight? Here's another reason why there's inequitable, uneven distribution of heat. And it has to do with like area and the fact that Earth is curved. Earth's not flat. Earth is curved. No, it's not. Earth is curved. We're not going there. Stay on topic here. Imagine that this box right here, stay with me. Let's say that this box right here had like, say, 100 joules of energy from the sun, just to make up a number here. And here's another box, also has 100 joules of energy. And here's a third box with 100 joules of energy. If you're at the equator, these rays hit the Earth more or less straight on. And so that means that this box of energy, let's call that, say, 40 meters squared. I know it's not 40 meters squared, but here there's 40 meters squared that uses 100 joules of energy. But right here, you see how the Earth's surface, because of it being curved, there might be 60 meters squared. With that same sort of distribution, but due to the curvature of the Earth, it has to spread out over more territory. Well, that means that the ratio is off. Here, you had $100 to share amongst 60 people, as opposed to $100 to share amongst 40 people. Just based on its location, the equator actually gets better energy and more concentrated energy. That's probably the word I should use. It's more concentrated because it's not so extreme, the curvingness. I'm not a really good artist here, but if you kind of get what I'm going for, that same box of energy right here, as it hits the top of the pole, it has to spread out over way more area because of the curving of the Earth. So again, life's not fair, especially when it comes to the Earth and energy. Now, there's a few other things that affect how energy moves around on Earth as well. I just finished talking there about radiation. All of that was the sun sending its radiation to the Earth, and it's really not fair how Earth gets different sets of it because it depends on the time of year, depends on where you are. But now that energy is at the Earth, it can do things like conduct and undergo convection. And we need to understand the concept of atmospheric pressure before we move on. Okay? Atmospheric pressure is basically the idea that there are particles all around us running into us. We don't necessarily notice it, but there are air particles just floating around this room, and they're hitting you. Now, you know when we do notice air particles hitting you? When it's windy, right? When it's really windy in southern Alberta and air is hitting you, and you're trying to walk into a headwind and you're getting kind of blown back a little bit, I think then we notice particles of air. But this maybe is a good illustration here, is that there are just particles of air kind of here, there, and everywhere. By the way, why are there more particles of air closer to the Earth's surface than there are up high? Yeah, gravity. Thank you for whoever jumped in there as well. Yeah, gravity. We know that gravity has a stronger effect the closer you are to things, which is why astronauts on the International Space Station way up high in the atmosphere, there's less gravity up there. There's actually less gravity at the top of Mount Everest than there is closer to the Earth's surface. So there are more particles down here. It is more dense, if I can use that word. There's more density close to the Earth's surface. Okay. Now, all of these particles are running into things and hitting things, and so therefore I would say that right now there's a lot of high pressure because there's lots of particles here. Okay. Now, here's a picture of something that maybe you're familiar with if you ever watch like the weather person on TV. You get like the H and the L for high and low pressure systems. Here's what that means if you've never heard this before. A high pressure system means that there are a lot of particles by the Earth's surface. So many that it's very pressurized. Well, those particles want to spread out, and so in general they spread out to the side, meaning that they create wind patterns that go away from you. High pressure systems involve a wind that is traveling away from you as these particles try to spread out. Opposite to that, a low pressure system is where you don't have quite as many particles as you'd expect. And if you have low pressure, particles rush in to try to fill in the gaps. You guys know a vacuum. We've talked about vacuums before in science, right? Well, this might not be a true vacuum where there's nothing there, but you know how like you open up a can of something and you hear it go whoosh? You're hearing the air whoosh into the can because there was kind of a gap there. There was a lack of oxygen, or just air in general, and particles are going to whoosh in. That's a low pressure system. Okay. Now, the one thing I didn't talk about though is the arrows that are coming down are going up. That's on my next slide. We need to add one more thing to this. Sure, we have high and low pressure systems, but what does hot and cold air have to do with it? What does hot air in red here do? Hot air rises, right? So now we have to compare not only side to side direction, but up and down. Hot air likes to rise. Well, what happens to that hot air once it rises? Eventually it cools down. As it cools down, though, it's going to kind of move a little ways, and eventually it'll cool back down, and then it'll come back over here, get hot, and rise again. We can actually create convection patterns. But it's not just about the hot and cold air. It's also about the high and low pressure systems. What do low pressure systems want to do? Well, low pressure systems have very few particles, so everything wants to come towards the low pressure system. High pressure systems have lots of particles. So what happens in a high pressure system? Everything wants to go away from it. And that's how you get this convection current going on, where a low pressure system lacking particles gets warm. They rise up in the air. In the meantime, other things come in and take their places. Those particles cool down. As they cool down, it becomes heavy in a high pressure system, and then they want to scatter in all directions. and it creates this loop. This is a convection current loop. And it creates wind. Because if you were standing right here, you're going to feel a wind coming that way. A wind always goes from a high pressure system to a low pressure system. And now you can feel the wind moving. And that wind, with it, is carrying energy. Okay. In general, here's a basic rule. Temperature is always lower the higher up you go. The higher up in altitude you go, usually the colder it is. Look, here at 1,000 meters, it's 24 degrees. 2,000 meters, 17 degrees. 10 degrees at 3,000 meters. Which makes sense, though, because it's really hot right here, and as the hot air rises, it eventually becomes colder, so it can fall back down again. It does seem a little backwards, though. You might think, shouldn't the top of the mountain, shouldn't that have the most amount of energy coming from the sun? Isn't that the closest part to it? But one thing that I've missed is that, what color is the snow? White. What do white things do? Absorb or reflect? Reflect. So all of that solar radiation that we would like to have melt the snow isn't actually melting it because it reflects it. We're going to need snow to melt based on conduction and convection. But how many particles are there way up high in the atmosphere? Not as many. So that's why we actually have the snow at the top of the mountains. Unless you have this weird phenomenon. It's called an inversion. Inversions happen where somehow you end up reversing and you get cold air trapped close to the ground. You have like warm air and then cold air like you'd expect, but somehow you got cold air kind of below the surface. We see this in the river bottom in Lethbridge. You ever see a really foggy day and it's really like there's a lot of like fogginess down at the bottom of the Old Man River there? That's what we're seeing right here. Here's the coulee. Here's warm air, on top of Whoop-Up Ridge. Here's cold air above there, but below Whoop-Up Ridge was some cold air. And so that's why you might see that as like a steam, or what you're really just seeing is water vapor. You're seeing H2O in its vapor format because it's really cold down there. Okay, moving on. Next topic we want to discuss is called the Coriolis effect. Not only does different places on Earth get different unfair amounts of energy, not only does that energy move around a lot, but the Earth is spinning. And the fact that the Earth is spinning does something. Okay? This is not a very accurate picture, but it gets me started on the topic, so bear with me for a second. Where is it warmest on Earth? Probably the equator. So what happens? Warm air at the equator rises. That must be a low pressure system because everything is rushing in towards the equator. Then the warm air that's rising tries to find somewhere to cool down. Where's the coldest place? Probably the North Pole. So the cold air heads towards the North Pole, which is now probably a high pressure system, and that tries to force the air back again. And in theory, it would make sense to have a convection current where warm air rises to the equator, makes its way to, North Pole, comes back again. That would mean, though, that all of our winds are running towards the south, always. It would mean always that we have wind heading south. That's not what we see, right? Very rarely, actually, do we get a wind that's going directly due south. A lot of times they're heading in weird directions. Here's why. It has to do with Earth spinning. Okay. If Earth is spinning, which it is, if something was trying to travel due south, because the Earth is spinning, it actually causes it to just tilt slightly sideways. It bends it because of the spinning of the Earth. The same thing happens from the South Pole. If a wind was coming from the South Pole towards the equator, because of the Earth spinning, it would actually deflect slightly off to the side. And what we've learned then is that most things in the northern hemisphere start to spin in a clockwise circle. Most things in the southern hemisphere tend to spin in a counterclockwise circle. And we can see this, and I'm going to show you some pictures in a little bit, but we can see this in natural wind patterns. Because otherwise what would happen is we'd only ever have wind heading towards the equator. And that's not how things work. Okay. Here's another picture to help illustrate the point. Because of Earth spinning, if you tried to throw something right here, throw it that way, but if you're spinning, it would actually kind of veer a little bit to the side. It's almost like throwing a football into the wind. Right? Imagine that I want to throw a football like this, directly straight, but it's really windy. Well, the wind kind of pushes the football to the side. Only we're not talking about wind here, we're talking about the Earth itself is spinning. Because the Earth is spinning, it deflects off to the side. Okay. Here's my best picture. This is what creates what we call the trade winds. Okay? There are many winds that we have on Earth, but most of them don't actually go north-south, like the picture I showed you. Because here's what really happens. Here's the equator. Warm air at the equator rises. as the warm air rises, it tries to head northward, but it doesn't make it all the way to the equator. Okay? This picture over here is a little bit much. This warm air is not going to go all the way to the North Pole before falling again. That's just, it's not realistic. But what can happen is this warm air will rise. It'll try to make its way to the North Pole. Eventually it'll fall and come back down. However, because the Earth is spinning, it causes these winds to start deflecting a little bit to the side. And you can see right here, you see how all of these winds right here are starting to make a bit of a circular pattern? There's also a very common one over here on the other side here of North America, where there's kind of a circular wind pattern. But check out the southern hemisphere. In the southern hemisphere, the winds kind of head the opposite direction. There's actually counterclockwise winds. Does that make sense at all? So these are known as our trade winds right here. Okay. There's actually some really common ones that blow from the west as well and down here. And that's just due to this one right here merging up with this one, like right here. So I think that's probably enough for us to work on for right now. The other type of wind that we should know about is something called a jet stream. Jet streams are winds that are not on the surface of the Earth. They're way up high in the stratosphere. And what makes these really cool is that this jet stream that we've discovered, it travels 250 miles an hour. Really useful if you're flying from New York to London. Because if you can get your airplane in the jet stream, now you're traveling with the wind. Right? Now, if you're traveling from London back to New York, I would highly recommend not trying to fly into a jet stream. One, because you're going right into the wind. Two, you'd probably crash into the airplane that's trying to go the other way. So you probably want the airplane from London to New York to maybe travel along that route instead. It would, yeah. But wouldn't it make more sense to take a slightly longer way than to fly right into the wind, especially a 250 mile an hour wind? This is found in the stratosphere, by the way. And one more thought here. Why do jet streams occur? Stay with me here. Less friction due to high altitudes. There is less air particles up high in the air because you're further away from the Earth. Gravity has less effects. So there's less friction the higher up you go. So if you can get yourself into one of these jet streams, traveling the right direction, you can actually make your air travel really cut down on the amount of time it takes. But only if you're traveling in the right direction with the jet stream, obviously. All right, next concept. Not only can we have convection currents that are based on air, we can also have convection currents based on water patterns. Now, the only difference here is that when I showed you this map about 3 slides ago, let me find it again here. Here's my slide about 3 slides ago. Yeah, I'm trying to talk too fast. See how some of these winds are going over the surface of continents? Well, that's because wind can travel over land and over sea. But if we're talking about water patterns, like I'm trying to right here, these can only travel in the water. But you'll notice the same sort of patterns occur. See how all of these right here are traveling clockwise, whereas these ones right here are traveling counterclockwise? There are very distinct patterns due to the Coriolis effect of the Earth spinning that cause these patterns of either clockwise or counterclockwise. You seen Finding Nemo, the movie? You know, Crush, the big sea turtle, and how they get into the big jet stream of water, you know, in order to travel faster. There's a very famous one that takes you from Australia to North America that travels basically like this. This is Finding Nemo right here. And if you can get in that path right there, you can get from Australia all the way up to, where did he have to get back to? Wasn't that like San Francisco or something like that? Wherever the dentist office was? I thought it was from Sydney? Oh, okay, well then we do the opposite then. Remember how it goes in a circle? If they have to go to Sydney, then you take this pattern like this, right? Because there's all of these circular patterns that are going there. So anyways, that's what I want to point out. These are not an exact match though, right? This slide and the slide 3 slides before are not an exact match because these currents can only go in the water, whereas wind can go anywhere, right? If I can go back a slide here, just to point that out here. These trade winds are actually how Christopher Columbus made his way to North America. You guys know the story of Christopher Columbus, right? It comes from Italy, Spain, over here in Europe, right? He would have used the trade winds, something like this. He would have come from over here. He would have used the trade winds to blow over to here, and that's why he kind of landed in the Central America area, and that's why many explorers eventually landed in Florida, if not, you know, somewhere in the Mexico, Central America, South America region as they discovered the Americas coming on these trade winds. So, because what was pushing the boats? Their sails, right? Oh yeah, 2 more things, then we're done. I got to make sure I time this well. There's also a unique weather pattern that occurs at the boundary between water and land. Okay? Land, by virtue of it being land, has the ability to absorb infrared. Right? We've just talked about how certain things absorb infrared. Green grass can absorb all sorts of different colors as well as infrared, and that means it heats up. What does warm air do? Warm air rises. It'll then migrate out towards the sea. It'll cool back down, and here's what I'm trying to get at here. If you are near the ocean and you are standing at the ocean, your feet in the sand, facing the ocean, you probably have a breeze at your face. Probably, most of the time. And the reason why is that warm air from the earth rises and the breeze comes in from the sea. We always name a breeze based on where it comes from. So we call this a sea breeze because the sea is bringing air towards us. But here's what's weird about that. What happens when there's no more sun anymore? Remove the sun and make it nighttime. Now there's no more radiation hitting the land, and what ends up happening is the land actually cools down much faster than the ocean. The ocean actually remains relatively warm compared to the land. So now as a comparison, the sea is now warmer. Well, if the sea is now warmer, air goes this way, down this way, and comes back this way. If you were, again, standing on the docks at night, you're probably having the wind come from your back. So during the day, the wind usually comes towards the shore, and at night, the wind usually goes away from the shore. And these are some more pictures to help illustrate that. At night, no radiation from the sun. You've got a moon, but that's not doing anything. The sea is warmer. Air goes up, creates a convection current, drops back down. If you're standing over here on the docks, the wind is at your back. But if it's during the day, the land is getting irradiated by infrared rays, causing it to heat up, and it goes the opposite direction. How do we name a breeze? Based on where it comes from. Okay? So if we have a sea breeze, the wind is coming from the sea, not to the sea, from the sea. So this is a sea breeze. Sea breeze happens during the day, land breezes at night. We're almost done, I promise. Yeah? Probably. Yeah, I'm not a climatologist, so I don't know the answer for that for sure. But my guess is probably. Again, these are climate rules because on any given day it could change, right? Right? I'm not promising that every time you go to the ocean it always works that way, but that's climate. Okay. Okay, last thing. Since we've been talking about climates, we can actually make we call these climatographs, and it's basically a nice little pictorial graph that helps you to I don't know, get a concept of what the climate is like in different locations. It's just best if we just look at these and talk through them here. It's pretty straightforward. This is Australia. When is it coldest in Australia? Look at the little red lines right here. It's actually coldest in Australia in June, July, August. But that makes sense though. Australia's on the other side of the world. They have the opposite seasons than us. When we think it's summer, they have winter due to the tilt of the Earth's axis. When do they get most of their rain? They actually get most of their rain during their winter months. We try a few more of these, just because I'm running out of time. Here's Vancouver, British Columbia. Vancouver, BC has most of their temperature during May, June, July, August, what we call summer. But when does Vancouver get most of its rain? During January, February, and November and December. Compare that to where we live. I couldn't find Lethbridge, but I found Medicine Hat. Medicine Hat or Lethbridge, more or less the same place. Except we're way better. Let's not forget that. Anyways, sorry. We have high temperature during May, June, July, August, but we get most of our rain during May, June, July, August. Okay. 2 more to compare to, then we're out of here, I promise. What about Halifax? Halifax is on the east coast of Canada. They also get most of their temperature during May, June, July, August, but they get most of their rain during January, February, and November, December. Last one, because this really helps illustrate the differences. This is Iquitos, Peru. Where is Peru? The equator, yeah. Way south, down by the equator. Check out the line for temperatures. It's flat. Why is it flat? Because there's no seasons at the equator. It's always summer, I guess. Right? Like it's always warm. There's no reason for up and down temperature variety because they get a nice constant amount of sun, so they get the same temperature. However, that's not quite the same thing for their rain. They actually do have kind of two seasons. Some places have what's known as the wet season and the dry season, where their wet and dry don't even correspond with what we might think they are. It's wet during what we would call spring, and it's dry during what we would call late summer, just based on when the temperatures happen to, when the rainfall happens, right? And rainfall happens based on precipitation being evaporated up into the clouds and eventually falling back down again, that hydrological cycle. So, okay, that's my lesson. One last thought before you guys take off. Try to work on your reflections and your practice questions now for lessons 2 and 3. Okay, you get a week before I close the reflections. So you have some time, but don't procrastinate. Please reflect on what we talked about. Sound good? All right, Bell should be going any minute here. Thanks, everybody.